This series is particularly for you to help regarding how to solve NAT and MSQ questions. You see, in the recent past, we have had these two questions coming up in GATE examination. NAT stands for numerical answer type questions. MSQ stands for multiple set questions. So over here, our aim is to understand what category of questions come over here and what techniques can you employ to solve these questions easily. Okay. The first set of questions will be MSQ questions, multiple set questions. Now the problem with multiple set questions is even if you get one option correct, it is not sufficient. You have to get all the correct options possible in that particular question. Okay? Let us get started. We are starting with fluid mechanics today. Okay. Let us start with the first question over here. The question is saying which of the following property or properties. Now very commonly whenever MSQ questions are there, they will indicate to you by mentioning something like this. Property or properties means it is possible that multiple answers are correct over here. So which of the following property or properties decrease with increase in temperature for liquids? Now you see, this is particularly for liquids he has mentioned. Okay. So the question is saying as temperature increases, which of these properties are going to decrease, particularly for liquids? Let us start. Dynamic viscosity, we know it is supposed to decrease with increasing temperature. You must have observed the stickiness in oil would decrease if you increase temperature. Kinematic viscosity also decreases. Surface tension is by the virtue of cohesion primarily, so surface tension also decreases. Vapor pressure, if you recall, vapor pressure is going to increase with increase in temperature, so this is supposed to increase. So now the correct answer over here is option A, option B and option C. You see, this question was a 1-mark question, theoretical question. It is based on the properties. One very important nature of property is variation with respect to temperature. For every property, try to understand how the variation with temperature is going to influence. Next question over here. Let us come to this question. Now you see the question is saying which of the following statements is or are true. Again he is mentioning over here is or are, indicating towards more than one answer can be correct. Which of the following statements is or are true for streamlines in a steady incompressible flow? Steady incompressible flow. First statement over here, two streamlines cannot intersect each other. This is a correct statement because intersection implies that you are having two velocity vectors at a particular point, which is not possible. Okay, therefore intersection of streamlines is not possible. Second statement over here, flow rate increases between two diverging streamlines. Now you see, you are having diverging streamlines over here. As you go forward, the area is increasing. He is saying flow rate increases. Now this is actually wrong. Flow rate is supposed to remain constant because if it is an incompressible flow, if I take two sections over here, whatever is a discharge taking place over here, same discharge is taking place over here. We know continuity equation in the case of incompressible flow is the value of Q influx and Q efflux, both of them are supposed to be same. So if I take this as my control volume, this Q influx must be equal to Q efflux. So therefore flow rate does not increase. What can change over here? It is possible he mentions velocity changes. Yes, it should change because it is diverging. What should happen as you go forward? The velocity is supposed to decrease on account of increase in area. Anyway, this statement is wrong. Flow rate decreases between two diverging streamlines. This also is wrong. Flow rate is supposed to remain constant. That is what we have discussed. Stream function has a constant value along a streamline. This statement is correct. You see, stream function, we are defining a function such that its value remains constant throughout a particular streamline. So the correct statement over here are option A and option D. Let me step aside. Option A and option D over here are correct. As a matter of fact, since we have spoken about stream function, let me also tell you the difference in stream function gives you the discharge per unit width between two streamlines. Okay. Moving further, again a 1-mark question, theoretical question. You see, whenever theoretical questions come, and mind you, GATE examination has started to take a lot of interest in theoretical questions because of MSQ. One good way of creating MSQ is to create theoretical question. So give good importance to theory also. Okay. Moving further. Now this question over here, slightly the print has been tampered, but let me explain you the question over here. The question says a pump draws water from a reservoir and discharges to an overhead tank. So you are having a reservoir over here, you are having an overhead tank over here. Okay. The area of the outlet pipe is 20 centimeters square. The average velocity of the outlet pipe is 3 meters per second. So cross section area over here he has given, that is 20 centimeters square. Average velocity also is given. Neglect minor and major losses in the piping. That means the flow is assumed to be ideal. The combined efficiency of pump and motor is 75%. Okay? Let me write down the given data over here. The data over here is the cross section area in second pipe is equal to 20 centimeters square. The velocity of flow over here, average velocity of flow at the outlet is equal to 3 meters per second. The combined efficiency of pump and motor is equal to, 1 second, I made a mistake over here, in 1 second please. Meter per second. Efficiency is equal to 75%. The working fluid is water. It is mentioned. Now look at the options over here. The question is saying which of the following statements is or are true. Again indicating towards multiple answers may be correct. The first statement over here, total head developed by the pump is 25 meters of water. Second is total head developed by the pump is 26 meters of water. Now guarantee at maximum any one of these can be correct. Both of them can't be correct. It is possible both of them also are wrong. Okay. But at maximum only one statement from here can be correct. Now look at the next two statements. The next two statements are power required to run the pump is 1.96 kilowatt. Power required to run the pump is 2.16 kilowatt. Again you see at maximum any one of these two can be correct. Now this is one more way of creating MSQs where they are asking you multiple concepts regarding a particular question. Okay. For example, if I wanted to make an MCQ over here, I would have given 4 options. All of them are based on the first and second concept only. That is first and second option only. But over here I have given 2 options based on head developed, 2 options based on power required. Now strictly speaking, similar kind of questions used to appear in GATE examination before also in the form of linked answer type. There used to be questions called as linked answer type where they would give you some information. Based on that information, they would ask you question number 1. After getting question number 1 solution, you had to attempt question number 2. Now you see question number 1 and question number 2 have combined into a single question. This is like question number 1. These two are representing question number 1 over here. These two are representing question number 2 over here. I hope you are following. Try to understand the psychology of examination. The more you understand the psychology of examination, the better prepared you are for attempting it. Anyway, let us come back over here. So we have to identify 2 things over here. How much head is being developed by the pump and what is the power required to run the pump. Let us go back to the diagram we have at hand. You see over here, there are some heads also given. You see the diagram over here is supposed to extend further down. Okay. This level over here, this level over here, this level over here, this level over here, this level over here. This is what we are having. Okay. Now to answer this, what I am going to do is, I am going to apply Bernoulli equation between 2 points. Let us say this is point A. Always prefer points in Bernoulli equation such that multiple terms can get cancelled off. I am taking this as point A and the point exposed to atmosphere over here as point B. What is the advantage in taking these 2 points as my points of Bernoulli equation? The advantage is point A and point B, both of them are exposed to atmosphere. Both of them are in a reservoir, in a container, big container. Therefore, pressure is also 0, atmospheric gauge pressure is 0 and the velocity is also 0. So if I take these 2 points, I can now write down over here, 1 second. I can now write down that the value of P1 by gamma plus V1 square by 2g plus Z1 must be equal to P2 by gamma plus V2 square by 2g plus Z2 plus head loss. Now since pump is there, we write minus HP. Now let us cancel all the terms which are not present. Anyway, the pressure terms I can cancel off over here. The velocity terms V1 and V2 also I can cancel off over here. Since the flow is ideal, head loss is cancelled off. The value of HP now comes out to be equal to how much? The value of HP over here comes out to be equal to Z2 minus Z1. HP is equal to Z2 minus Z1. All I have to do is identify the value of Z2 minus Z1. Let us come back over here. Now, forget about all the other points. Just try to climb from here to here. Now, Z2, basically this is 0.2 for us. This is 0.1 for us. Z2 over here, Z1 over here. So from here I go till 5 meters, then I go till here, 20 meters. So 5 plus 20 is 25. So since it is 25, I can say this value is equal to 25 meter of water. This value is equal to 25 meter of water. Pump is supposed to develop a head only of 25 meter over here. It is supposed to develop a head of 25 meter. So since it is supposed to develop a head of 25 meter, option A over here is correct. So I can say this option over here is correct. Okay. Now option B guarantee is wrong. Since option A is correct, option B has to be wrong. Now power required to run the pump. So basically this is the input power supplied to the pump he is asking. What is the power you are using, you are supplying to the pump he is asking. Now I can say over here, pumping power is equal to how much? 1 second. Pumping power is equal to how much? Pumping power is equal to gamma into Q into HP. Gamma into Q into HP. That means this is the amount of power pump is supplying to the fluid. Let us calculate. Gamma over here is equal to 9.8. Since he did not mention, I'll take standard value of gamma, 9.8 kilonewton per meter cube. Okay. Discharge over here is equal to area times velocity. Area is 20 centimeters square, means 20 into 10 power minus 4. Velocity is equal to 3 and HP over here is equal to 25. If I calculate this thing, if I calculate this, 9.8 into 60 into 25, it is coming out to be 1.47 kilowatt. So this is coming out to be 1.47 kilowatt. That means the pump is supplying this much power. To whom? It is supplying this much power to the fluid. But he is asking what is the input power to the pump. So now the power to pump has to be equal to the power by the pump divided by efficiency. Divided by efficiency. Because when it comes to pump, you think about pump now. From pump's point of view, this is this power to pump is the input, and this is pumping power is the output over here. So efficiency is equal to output by input. From here, this is what we are getting. So this value happens to be equal to how much? This value is equal to 1.47 divided by 75%. 75% means 0.75. So if I divide it by 0.75, I am getting this value as 1.96 kilowatt. It is coming out to be 1.96 kilowatt. So if you see over here, do we have 1.96 kilowatt? As a matter of fact, we do. The correct answers over here are option A and option C. A and C are correct over here. So one category of question in MSQ is they'll give you some data, they'll ask you multiple things regarding that data. Okay, no? That is one kind of question in MSQ. Let us move further now. This is a very good question. Very, very good question. It has a slight touch of mechanics also with it. The question is saying two solid spheres A and B of equal volumes but of different densities dA and dB are connected by a string. They are fully immersed in a fluid of density dF. They get arranged into an equilibrium state as shown in the figure with tension in the string. The arrangement is only possible if, over here if you see, there are multiple options present over here, okay. You have to check all of them now, okay. Let us see how to solve this particular question. Now let me show you some key points over here. Some key points over here. They are arranged into equilibrium. So system is right now in equilibrium with a tension in the string. That means the tension in the string is not equal to 0. You are having a non-zero value of tension in the string right now. So this is the arrangement we are having. We have to identify which of these options are true. Let us get started over here. If you want, I'll give you half a minute. Please draw this diagram, mention the options also, because I'm going to move this further. Chaliye, let us get started. Now, what I'm going to do is, I'm going to draw the free body diagram of this particular system. I'm going to draw the free body diagram of this particular system. If I draw the free body diagram, I'm having this as A, this as B over here, A and B, let us say. Both of them are having equal volumes, okay. Now, if I draw the free body diagram of A, first of all, weight force is acting down. This is weight of A. FB is acting up. This is FB, force of buoyancy on A. And since it is above and the cable is below, the tension acting over here is like this. The tension acting over here is like this. Now coming to the lower body, you are having weight of B acting this way. Force of buoyancy on B is acting this way. And the tension in the cable is acting up over here. This is what I'm having. This is what I'm having. Now remember one very important rule in mechanics. If a system is in equilibrium, a portion of a system also must be in equilibrium. That means if this entire system is in equilibrium, a part of it, let us say only part of A or only part of B, they must also be in equilibrium. That is a rule. Okay. Now, let us get started first of all with this particular body. With this body, I can say over here, WA by equilibrium, WA plus tension has to be equal to force of buoyancy on A. That means WA over here is lesser than force of buoyancy on A. WA over here is less than force of buoyancy on A. Since WA is less than force of buoyancy, mind you, volume of A and volume of fluid displaced, both of them are same. Therefore, I can safely say over here, the density of A is less than density of fluid. First thing I can say over here, density of A happens to be less than density of fluid. Let us see, do we have any options supporting this? Density of A less than density of fluid. As a matter of fact, we are having this option over here. This is option A. Is correct. Now let us talk about the second. Let us talk about the second body over here. If I talk about the second body over here, what do we have? We have, by equilibrium, weight of this body WB must be equal to the upward forces, which is force of buoyancy on B plus tension. That means weight of body is greater than force of buoyancy on B. Now if you observe over here, weight of body B is greater than force of buoyancy. Again, volume of body and volume of fluid displaced, both of them are same. From there I can say density of body B must be greater than density of fluid. I am having one more result over here, density of B greater than density of fluid. So from here I get this particular result, density of B greater than density of fluid. Now, guarantee option C is wrong, because if option A is correct, option C over here is wrong. Now I have to check whether this option D is correct or not. To check whether this option D is correct or not, what I am going to do is, I am now going to speak about the complete setup. If I speak about the complete setup, means combination of both of them. Now bear in mind the volume of body A and volume of body B, both of them are same. That basically means FB on A and FB on B, both of them are also same. Okay, now so now if I take the complete setup over here, the equation I'm going to get is all the upward forces must be equal to downward forces. Tension T downward and tension T upward will get nullified. They become internal forces for the entire setup. So I'm having over here WA plus WB going down. WA plus WB going down must be equal to FB plus FB, that is equal to how much? 2FB over here. That is equal to 2FB over here. Now WA, because both the FBs are same, mind you. Now if I divide by volume throughout and G throughout, I am going to get density of A plus density of B is equal to, because volumes are same, G is also same of course, it is equal to 2 times density of fluid. Density A plus density B is equal to 2 times density of fluid. Let us check, do we have any options supporting that? As a matter of fact, we do. So we see over here, density A plus density B is equal to 2 times density of fluid. So the correct answers over here are option A, B and D. So now in this question, you see, you are supposed to identify, you are supposed to check each one of these options and check whether they are correct or not. So these kind of questions can become very lengthy. Okay, so my advice to you, when you find questions of this sort where you get a particular given data and you have to keep checking each one of them, this can take a lot of time. So better skip these questions temporarily. Once you have finished easier questions in the paper, you can come to these kind of questions. It is a very important skill to identify what kind of questions will take a lot of time. You will always find few questions in examination which are thrown into the paper just to trouble your time. Once your timing is troubled, then automatically you feel demotivated as you go further in the paper. So that is also a test actually. So always look for questions which are more theoretical, which are more, direct questions first of all. Then you can go for those lengthier questions. Look at this, look at this question over here. The question is saying, the flow has a velocity potential given by phi is equal to ax cube. Excuse me. Where A is a non-zero constant, which of the following statements is or are true about this particular flow? Now you see, he is mentioning over here, flow is incompressible, irrotational, local acceleration is there, convective acceleration is there. 4 options are given over here. Now to answer these things, I have to identify both the components of velocity. I'm assuming it's a planar flow over here. Okay, I have to identify both the components of velocity. So now how do I find out both the components of velocity over here? I can say over here, the value of phi is equal to ax cube. The value of u has to be equal to dou phi by dou x, and the value of v is equal to dou phi by dou y. Dou phi by dou y. If you think about it, phi is not a function of y at all. Therefore, the component v over here is equal to how much? 0. The value of u comes out to be equal to how much? U comes out to be equal to over here. Since it is ax cube, this becomes 3ax square. 3ax square. Now, if you are very smart in the concept of kinematics, you can straight away say this is not a case of incompressible flow. This is actually compressible flow, and it is not a. It is a case of irrotational flow. But then again, why and all? If you are very fast in kinematics, some questions you can answer orally, and you can also answer over here. Option D is correct. Option C is wrong. So I am straight away answering just by looking at this. Answer is B and D over here. Okay. But then let us check now. I got this orally just by looking at this particular equation. How so? Because my velocity vector over here, 3ax square है. My velocity vector over here is equal to how much? 3ax square I cap plus 0 j cap plus 0 k cap. This is my velocity vector I am having. To check whether it is a case of incompressible flow, you have to check dou u by dou x plus dou v by dou y plus dou w by dou z. If you check this value, these terms will get cancelled off over here, but dou u by dou x becomes equal to 6ax, which is not equal to 0. Therefore, the flow happens to be compressible flow. Option A, which was saying incompressible, is wrong. Next thing, I personally have a logic that rotation and shear is possible when a component of velocity varies with respect to perpendicular axis. Right now, this is component in x, function only of x. That means linear strain is possible, rotation and shear is not possible. If you have attended my classes, you know this statement. Before starting the concept of deformation, rotation, I always mention this particular statement. When is deformation possible? When is linear deformation possible? When is shear possible? When is rotation possible? When is shear without rotation possible? When is rotation without shear possible? All these things we have discussed. अब orally बोल सकते हैं आप, you can tell this orally, when velocity in x is a function only of x, linear is taking place, shear or rotation is not taking place. So therefore, I can say the flow is irrotational. If you wish to find out how, by equations and all, you can identify by vorticity x, vorticity y, vorticity z, all of them you will get as 0. Next thing, local acceleration demands the velocity to be a function of time. Right now, velocity is not a function of time. Therefore, local acceleration is not present. Convective acceleration, is it present or not present? It is present over here, because if you calculate the value of ax is equal to how much? Dou u by dou t plus u into dou u by dou x. I am stopping at this only. I can go further with v into dou u by dou y and w into dou u by dou z. There is no point because y and z are not present in this particular flow right now. So this value anyway is equal to 0. If you see u is existing, dou u by dou x also is existing from here. So therefore, convective acceleration is present. The correct answers over here are flow is irrotational and flow has convective acceleration. I hope this is clear till here to all of you. Let me take one more question from the concept of this multiple set questions. In a pipe network, he's saying which of the options are correct. Multiple options may be correct over here. The influx and efflux of discharge must be same at any node. Yes, true. If you remember, pipe network was a topic we had in flow through pipes. Okay, over there we mentioned two rules. One was for node, one was for a loop. For node, the ruling was influx and efflux have to be same, because we always assume in the case of pipe network the flow is incompressible. Next thing, the head at each node must be same. This is not true. The head at each node must be same is not true. Imagine कीजिए that you are having a building in which you are having a pipe network. One node is somewhere on top near the reservoir, one node is near the bottom. Both of them need not be having same head, of course. Next one, the algebraic sum of piezometric head drop across each elementary circuit is 0. In simple language, he is saying the head loss in each loop must be equal to 0. That is correct, because when you're talking about a particular loop, you're starting from a point coming back to the same point. Therefore, the piezometric heads are going to be same initial and final. Therefore, the piezometric head drop or head loss, both of them are equal to 0. The piezometric head loss in each line of a circuit is the same. This is wrong. We never put this condition that along a line the head loss should be same. The correct answers over here are option A and option C. They can ask you numericals also on this. I have seen in XE paper especially, numericals have appeared from this particular concept. Let me move further. I will go for questions which are, let me finish one more question over here. 1 second. There was supposed to be one more option, it got trimmed off. Anyway, the question is saying, the figure shows a developing zone and fully developed region in a pipe flow where steady flow takes place from left to right. The wall shear stress at section A, B, C, D are given by tau A, tau B, tau C and tau D respectively. Select the correct statements were supposed to be there. Now you see, you should know in the developing region, as you go further, the shear stress keeps on decreasing. If it is a case of laminar boundary layer, you must recall, in the case of laminar boundary layer, if this is tau over here and this is x-axis over here, tau is inversely proportional, tau naught is inversely proportional to 1 by root x in laminar during developing region only. So you will have something like this. Once it has reached this developed condition, then it becomes a constant. It becomes a constant. So now tau A over here has to be greater than tau B, has to be greater than tau C, has to be equal to tau D, because C and D, both of them are lying in fully developed region. Therefore tau C and tau D have to be same. Okay, I am sorry, there was one more option, it got trimmed somehow. Anyway, once you know this thing, what all options can you choose over here? You can choose tau A equal to tau A greater than tau B greater than tau C. Tau C is not greater than tau D. Tau C and tau D, both of them are equal, because in fully developed pipe flow, if you recall, the equation of tau naught was given by minus dP by dx in case of a horizontal pipe, multiplied to R by 2, multiplied to R by 2. Now you see, minus dP by dx remains a constant, therefore tau naught also remains a constant in the case of fully developed region. So anyway, options over here amongst A, B and C is A and B are correct. I hope this is clear. Let us now move to numerical answer type questions. Now numerical answer type questions can become lengthy. They are purely numericals only. Okay? And one very important advice I would give you, I always give this advice in every class I take, is try to push the calculations as later in the numerical as possible. Avoid doing calculations early. What is the advantage of this? Many times when we do our calculations, we take into account some errors. Because we have to approximate. If let us say decimal places are going up to 14 digits, you can't take all 14, of course. You'll stop at 1 or 2. Okay, at maximum 3 sometimes. Let us say friction factor, I always suggest you to take up till 4 also sometimes. Okay, so now you have to stop at some decimals. In this, what you are doing, you are making an error. Now as you keep on putting this error in multiple steps and again doing calculation, the error gets compounded. That error will deviate a lot from the actual answer. That is why try to avoid calculations early. Of course, sometimes if it is not possible, you have to do calculations early, you have to do it, no problem. But if it is possible, try to delay the calculations, how much ever it is possible. Let us start. Question number 1 over here say, in measuring the surface tension of oil of relative density 0.5 by the bubble method, a tube of internal diameter 1.5 mm is immersed to a depth of 1.25 centimeter in the oil. Air is forced to the tube, forming a bubble at the lower end of the tube. Okay. What is the surface tension? What surface tension is indicated by maximum bubble pressure? He's asking. Okay. Now let me get started. 1 second, please. Fine. Let me get started with this particular question. The question is saying over here, I am having some container. In this container, there is oil of relative density 0.85. You are taking a tube of diameter. Okay, it is pushed down to a depth of 1.25 centimeter. Excuse my diagrams, please. I can't be very neat now. Okay, air is forced to the bubble. What surface tension is indicated by a maximum bubble pressure of 147 Pascal. So when you are blowing over here with a pressure of 147 Pascal, you are having a bubble formed over here. You are having a bubble formed. Now this question is basically talking about two concepts over here. Very good question, worth 2 marks in your examination. It is talking about two concepts. One concept is the measurement of pressure. The other concept is difference in pressure across a curved surface. Now let us say the inner pressure over here is Pi, which is equal to 147 Pascal. The outer pressure is Po, which is equal to gamma times H or rho GH. And difference in pressure across a bubble of air is known force sigma by D. So I can write over here, pressure inner is greater minus pressure outer has to be equal to the difference in pressure across a gas bubble is equal to force sigma by D. Force sigma by D. Okay. The value of inner pressure is given to us as how much? 147 Pascal. Outer pressure is by the virtue of hydrostatic pressure, it is gamma times H. Since the density is equal to 0.85, I can say 850 into G is equal to 9.8. H is equal to 1.25 centimeters, so 1.25 into 10 power minus 2. This is a value of P outer, has to be equal to 4 times sigma divided by the diameter of this particular tube is 1.5 mm. It is 1.5 into 10 power minus 3. 10 power minus 3. Let us solve this thing. If I solve this, excuse me for using this calculator. One second, yeah. I'm getting the value as 0.016. Please check. Sigma is equal to 0.016 Newton per meter. Now generally when they ask you numerical answer type, they will mention what units they want the answer in. Okay. I'm getting the answer as 0.016 Newton per meter. I hope this is clear till here. This was combining two concepts. Moving further. Let me take some questions which one minute please. This is a very good question. The print got tampered slightly. I will help you with this thing. The question is saying for a given location in a flow, the rate of change of density of a fluid particle, which is given by d rho by dt is equal to dou rho by dou t plus dou rho by dou t plus dou rho by dou x plus dou rho by, one second, it is supposed to be u into dou rho by dou x, u into dou rho by dou x, v into dou rho by dou y plus w into dou rho by dou z. Okay, this is what he has mentioned. The rate of change of density is given as this much. It is equal to, this is equal to minus 2.4. It is equal to minus 2.4 kg per meter cube second. Meter cube second. If the density of this at this particular point is equal to 1.2, density is equal to 1.2. Density is equal to 1.2 kg per meter cube. The divergence of velocity field, that is del velocity vector, is equal to how much he is asking in second inverse. Okay. Sorry, there is some trouble with this thing, but I hope I have mentioned over here. The time rate of change of density is given like this. It is equal to this much. Density is equal to 1.2. Divergence of velocity field is equal to how much? I have taken this question from XE paper long back. I think around some more than 10 years back this particular question came in XE paper. I have slightly changed numbers, and over there they gave options. I am not giving options over here. Okay. Anyway, let us see how to solve this particular question. Now to solve this particular question, you have to think of what equation shall we start with. Divergence of velocity vector is basically dou u by dou x plus dou v by dou y plus dou w by dou z. And this is indicating towards continuity equation, something related to continuity equation. So best thing to do is, let us start with continuity equation. We know by continuity equation, I can write over here dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w has to be equal to how much? 0. This is our continuity equation. Valid for every flow, whether steady, unsteady, incompressible, compressible, no matter whatever, it is supposed to be valid. This is the parent continuity equation we are having. Now what I'm going to do is, this each term over here, I'm going to use my UV rule to break it open. If I use my UV rule over here, this term is going to become rho into dou u by dou x plus u into dou rho by dou x. Likewise, let me put this as it is, dou rho by dou t plus this term is going to become rho into dou v by dou y plus v into dou rho by dou y. And lastly, the next term is going to become rho into dou w by dou z plus w into dou rho by dou z. This has to be equal to how much? 0. Now bear in mind, this value plus this value plus this value plus this value was basically time rate of change of density. That is capital dt, this entire sum of these, whatever I put in box, it was equal to capital D rho by capital dt. And this value we know it is equal to how much? It is equal to minus 2.4. So in place of all these terms, I'm writing this, then I'm writing plus, taking rho common for the remaining, rho into dou u by dou x plus dou v by dou y plus dou d by dou z. Ye kya hai? This is divergence of velocity field. Must be equal to how much? 0. This is what we are having. Are you following this? Now this value is given to you as minus 2.4. So minus 2.4. This value of rho is given to you at this particular location as 1.2 into divergence of velocity field must be equal to 0. Ab boliye answer kya hai? Very simple. This is supposed to be 2 now. The value of divergence of velocity field is equal to 2 second inverse. So our answer over here, divergence of velocity field is equal to how much? It is equal to 2 second inverse. I hope it is clear till here to all of you. Okay. This is basically another way of representing your continuity equation. Another way of representing your continuity equation. I hope it is clear till here to all of you. Let me take one more question now. I am not having a lot of time, so I'll be taking some selective questions over here, which I find are very interesting. Okay. Look at this particular question, very interesting question, slightly lengthy question over here. The question is saying two pipes, L1 is equal to 400 meter, D1 is equal to 30 centimeter, L2 is equal to 500 meter, D2 is equal to 20 centimeter are connected in parallel between two reservoirs. If friction factor F1 is equal to 0.02, F2 is equal to 0.015, then what difference in reservoir water surface elevation will produce a total flow of 0.25 meter cube per second from one reservoir to another reservoir? Let me explain you what is being asked over here. The question is saying you are having a reservoir over here, you are having another reservoir over here, you are having some elevation level over here, you are having some elevation level over here. Okay. Now you are having two pipes. You are having two pipes now. Okay. One pipe, let us say, 1 second. You are having two pipes over here. Now one pipe, let us say, is pipe 1. One pipe, let us say, is pipe 2. Now regarding pipe 1, he has mentioned for pipe 1. For pipe 1, he has mentioned over here, the value of length is equal to L1 is equal to 400 SI units, D1 is equal to 0.3 SI units, the value of F1 is equal to 0.02. For pipe 2, he mentioned over here, L2 is equal to 500 meter, D2 is equal to 0.2 meter, D2 is equal to 0.2 meter and F2 is equal to 0.015. 0.015. This is what is given. Now with this information he's asking you with this information, what is the elevation difference that is going to produce a net discharge? What is the elevation difference over here equal to? This head difference is equal to how much? If the net discharge over here is equal to 0.25 meter cube per second. Difficult question, lengthy question. Such a question you see in examination, first thing, leave it initially. Okay, because you might solve this question, it takes a lot of time actually. Fine. Anyway, how to proceed with this thing? Parallel connection. What is the rule for parallel connection? If you recall, the discharges will get added up. So this is basically Q equivalent. The value of Q1 plus Q2 over here is equal to how much? 0.25 meter cube per second. The discharge get added up. Next thing, the head losses have to be same. So the value of head loss equivalent has to be equal to head loss 1 equal to head loss 2. Now first thing what I'll do over here is, I will use this particular relationship whenever you are having parallel connection. I prefer this particular relationship to identify the value of Q1 in terms of Q2. So once I identify Q1 in terms of Q2, this equation which is having two unknowns will become an equation only of one unknown. I can find out that particular Q. Once I find the Q, this value is basically equal to head loss. I can find the value of head loss also. So three steps over here. Step number 1, getting value of one Q in terms of other Q. Then getting a Q value. Then again going back over here to head loss value. How do I start now? I am going to start with H1 equal to H2. H1 equal to H2, 1 by 12.1 cancelled off. F1 L1 Q1 square by D1 power 5 is equal to F2 L2 Q2 square by D2 power 5. D2 power 5. This is what I am having. Now I can say over here the value of, one second, the value L1 by L2 is 4 by 5. L2 by L1 is equal to 5 by 4. 2 by 3. 3 by 4. 5 by 4. 1 second. 5 by 4. 3 by 4. 2 by 3. Q1 is equal to Q2 under root of. Okay. This is basically L2 by L1, 500 by 400. This is F2 by F1, 0.015 by 0.02. This is D2 by D1, 20 centimeter by 30 centimeter, whole power 5 under root, because Q1 square, Q2 square, I'm making it Q1 and Q2. This is what I'm having. Now let me use calculator. Let me use this calculator. I'm having over here square root of I'm having the value of Q1 is equal to 1.57 Q2. Q1 is equal to 1.5736. So let us say 1.574 Q2. अब देखिए, I can't skip this calculation further. I have to do this calculation now only. So I did this thing. Once I got the value of Q1 in terms of Q2, I can now say the value of Q1 plus Q2 is equal to net discharge Q. So Q1 is 1.574 Q2 plus Q2 is 2.574 Q2 has to be equal to how much? It has to be equal to 0.25. So I can find out Q2. I got the value of Q2 over here as 0.09714 meter cube per second. Once I got the value of Q2, I have done two steps now. Now I know the elevation difference between reservoir is nothing but the value of head loss. So now I can say the value of head loss is equal to, the value of head loss 2 is equal to 1 by 12.1 FLQ square by D power 5. This entire thing for second pipe. So this is 1 by 12.1 into F, I recall it was 0.015, length was equal to 500, Q2 is equal to 0.097 square divided by D power 5, it was 0.2 power 5. I am getting the answer as 18 over here. Can you please check what is the answer? I am getting the value of head difference is equal to 18.27 meter. 18.27 meter. Could someone please check? Fine. Okay. This is the value I'm having. Moving further, let me take this particular question. This is a very, very commonly asked question. I have seen this question in multiple branches paper actually. The question is saying laminar boundary layer takes place on a flat plate of length L. Find the ratio of drag force on first half length of the plate to the second half length of the plate. So you're having over here a plate, let us say, 1 minute. 1 moment please. I'm having over here a plate, let us say. This is the top view of the plate. The span of this particular plate is L, the width being B over here. He's asking if you break this plate down into two parts, not physically, but for calculation purpose. Let us say this is the first part, this over here is the second part. The question is asking what is the drag force on first part to the second part. Now recall the formula for drag force in the case of boundary layer theory was equal to how much? It was equal to B integral of tau naught dx. Mind you, I would take the integral from 0 to L if I want for the net plate, but right now I want for first plate and second plate. So if I take FD1 by FD2, I am going to have over here divided by B integral of tau naught dx. Again, now this is ranging from where to where? This is ranging from 0 to L by 2 and this is ranging from L by 2 to L. I can cancel off B by the virtue of B being constant. I am having integral tau naught dx by integral tau naught dx. They can't be cancelled. The reason being the limits are different over here. So what do I do now? I recall in the case of laminar boundary layer, wall shear stress is proportional to 1 by root x. We have seen this relationship also in development of flow question. Okay. So since tau naught is proportional to 1 by root x, I can do one thing. I can say over here FD1 by FD2 over here comes out to be equal to FD1 by FD2 comes out to be equal to integral of 1 by root x dx, that is x power minus half dx upon integral of x power minus half dx. This is ranging from x is equal to 0 to L by 2. This is ranging from L by 2 to L. Now x power minus half dx integral is going to give you x power half divide by half. That dividing by half can be cancelled off. If you put the limits, this is going to be equal to root over of L by 2 upon root over of L minus root over of L by 2. This is the answer. This is a value. If you cancel off L throughout, you are having 1 by root 2 upon 1 minus 1 by root 2. That is going to give you, if you rationalize this thing by multiplying 1 plus root 1 by root 2 on 1 plus root over of 1 by 2 in numerator and denominator, you will get the answer eventually as root 2 plus 1, which is equal to 2.414. This is a ratio. Since it is a ratio, it is dimensionless quantity over here. I hope this was clear. Okay. With this, I'll stop. I hope the questions taken over here were clear to all of you. If you need any help, we are always here to serve you. All the very best.